AC armored cable and MC metal clad are both essentially similar except for the bonding strip found in AC cable. AC is employed in scenarios where its jacket is susceptible to damage or cuts, such as hospitals and warehouses with forklift traffic. The bonding strip in AC cable serves to stabilize the jacket, preventing it from shifting and potentially severing the conductors inside. MC cable necessitates the use of appropriate fittings to ensure the cable's jacket remains secure. However, achieving this security cannot always be guaranteed. As a result, AC cable is frequently specified in these particular applications. AC is commonly used for larger conductors in industrial settings. AC armored cable features an outer steel armor that shields the conductors from physical harm. It is typically found in commercial and industrial environments where the cable is at risk of potential damage. MC metal-clad cable has a flexible metal sheath that encases the conductors. It is commonly used in residential and light commercial settings where the cable is not exposed to potential damage. The primary distinction between AC and MC cable lies in the type of external protection they offer. AC cable boasts steel armor that provides greater durability compared to the flexible metal sheath of MC cable. This makes AC cable a preferred choice for applications where the cable is vulnerable to potential damage. MC cable exhibits greater flexibility compared to AC cable, simplifying installation in confined spaces. Furthermore, it is generally less expensive than AC cable. In hospitals and other healthcare facilities, it is crucial to utilize cable that is damage resistant and capable of withstanding the demanding conditions of a healthcare setting. AC cable fulfills these criteria due to its robustness and ability to endure the chemicals and cleaning agents commonly used in hospitals. There is a concern regarding the possibility of a conductor coming into contact with the cable's armor. Because MC cable lacks a bonding strip, even with properly installed fittings that bond the armor to the equipment grounding conductor, there is a risk that the overcurrent protection device may not trip due to inadequate continuity throughout the interlocking armor. Consequently, it is essential to use the correct fittings when installing MC cable. These fittings must establish a reliable electrical connection between the armor and the equipment grounding conductor. If the fittings are not properly installed, the armor may not be effectively bonded to the equipment grounding conductor, potentially preventing the overcurrent protection device from tripping in the event of a fault. AC cable necessitates more stringent fastening requirements compared to MC cable due to its increased durability and ability to withstand greater force. These additional fastening requirements ensure that the cable is securely anchored and protected from damage. Considering the characteristics of each type of cable, the suitability of AC versus MC depends heavily on the specific application and environmental factors. In scenarios where physical protection and resistance to harsh conditions are paramount, AC cable is the preferred choice. Conversely, in situations where flexibility, ease of installation, and cost-effectiveness are key considerations, MC cable may be more appropriate. The National Electrical Code, or NEC, provides guidelines and requirements for the proper installation and use of both AC and MC cable. It is crucial to adhere to these regulations to ensure electrical safety and compliance. The bonding strip in AC cable plays a crucial role in maintaining electrical continuity throughout the cable assembly. This strip provides a low impedance path for fault current to flow back to the source, facilitating the rapid tripping of the overcurrent protection device in the event of a ground fault. Without the bonding strip, the impedance of the armor itself may be too high to allow sufficient fault current to flow, potentially delaying or preventing the overcurrent protection device from operating. This delay could result in equipment damage, fire hazards, or even electrical shock. The fittings used with both AC and MC cable are essential components of the overall wiring system. These fittings serve several important functions, including providing mechanical support for the cable, ensuring proper electrical connection between the cable and the enclosure or equipment, and maintaining the integrity of the cable's grounding path. The selection of appropriate fittings is critical to the safe and reliable operation of the electrical system. Factors to consider when choosing fittings include the type and size of the cable, the environmental conditions, and the specific requirements of the application. Proper installation of fittings is equally important. Fittings must be installed according to the manufacturer's instructions and in compliance with the NEC. This includes ensuring that all connections are tight and secure, and that the fitting is properly grounded. Improperly installed fittings can compromise the integrity of the wiring system and create potential safety hazards. The term overcurrent protection device, or OCT, refers to devices such as circuit breakers and fuses that are designed to protect electrical circuits from overcurrent conditions. Overcurrent can result from a variety of factors, including short circuits, ground faults, and overloads. When an overcurrent condition occurs, the OCT is designed to interrupt the flow of current, preventing damage to equipment and reducing the risk of fire or electrical shock. The selection of the appropriate OCT for a given circuit is critical to ensuring its proper protection. Factors to consider when choosing an OCT include the ampacity of the circuit conductors, the type of load being served, and the interrupting rating of the device. The interrupting rating of an OCT is the maximum amount of fault current that the device can safely interrupt. It is important to select an OCT with an interrupting rating that is sufficient to handle the maximum potential fault current at the installation location. Grounding is a critical aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, facilitating the rapid tripping of the OCT in the event of a ground fault. Grounding also helps to stabilize voltage levels and reduce the risk of electrical shock. The NEC specifies detailed requirements for grounding electrical systems. These requirements cover a variety of aspects, including the size and type of grounding conductors, the methods for grounding equipment and enclosures, and the requirements for ground fault protection. Proper grounding is essential to the safe and reliable operation of electrical systems. In addition to the specific requirements for AC and MC cable, the NEC contains general requirements that apply to all types of wiring methods. These requirements cover a wide range of topics, including conductor ampacity, wiring in damp or wet locations, protection against physical damage, and support and securing of cables. It is important to be familiar with these general requirements to ensure that all electrical installations are performed in a safe and compliant manner. The ampacity of a conductor is the maximum amount of current that the conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor is determined by several factors, including the size and type of the conductor, the insulation material, the ambient temperature, and the number of conductors bundled together. The NEC contains tables that provide ampacity ratings for various types of conductors under different conditions. It is important to select conductors with an ampacity that is sufficient to carry the expected load current. Wiring in damp or wet locations requires special precautions to prevent electrical shock and corrosion. The NEC specifies requirements for the use of approved wiring methods and enclosures in these locations. These requirements include the use of moisture-resistant cables, watertight fittings, and corrosion-resistant materials. Protection against physical damage is an important consideration for all electrical installations. The NEC specifies requirements for protecting cables and raceways from physical damage. These requirements include the use of conduit, cable trays, and other protective measures. The level of protection required depends on the location of the wiring and the potential for damage. Support and securing of cables is necessary to prevent strain on connections and to ensure that the cables remain in place. The NEC specifies requirements for supporting and securing cables. These requirements include the use of cable ties, straps, and other approved methods. The spacing between supports depends on the type of cable and the installation conditions. In summary, both AC and MC cables serve distinct purposes in electrical wiring, with AC cable favored for its robust protection in demanding environments like hospitals and industrial settings, while MC cable offers flexibility and cost-effectiveness for residential and light commercial applications. Adhering to NEC guidelines, selecting appropriate fittings, and implementing proper grounding techniques are crucial for ensuring electrical safety and compliance in any installation. Understanding the differences in bonding strips, fastening requirements, and the ampacity of conductors further contributes to making informed decisions for specific wiring needs.